Hi, my name is Nick Fazzari, and I'm on the research papers team here at MIT Sloan. Before I begin, I see we have some people kind of filtering in. There are seats in the middle, so feel free to make your way. I'm excited to present Panna Felsen, who co-authored, along with Patrick Lucy, who is in attendance, a paper called Body Shots, Analyzing Shooting Styles in the NBA Using 3D Body Pose Information. The talk will last 20 minutes, and we will have 5 minutes for Q&A afterward. So with that, Panna Felsen.
Hi, thank you everyone for being here. My name is Panna Felsen. I'm a PhD student at UC Berkeley, and this summer I interned at STATS. Today I'm going to talk about some of my work there. In particular, I'm going to talk about some joint work with Patrick Lucy on using 3D body pose to analyze shooting styles in the NBA. Now, over the last several years, STATS SportView has helped enable some great work with court vision from Goldsberry, ball screens from the guys at MIT, expected point value from the guys at Harvard, rebounding out of USC, and recent work from STATS on play retrieval. But we're starting to reach a limit in terms of what's possible with the trajectory data alone. What do I mean by that? So if we consider this shot, this three-point shot, from the perspective of the SportView trajectories, initially, this appears to be a very high percentage chance opportunity. The shooter's wide open when he receives the ball. But instead, he waits until his defender has closed out before taking his shot. Why does he do that? Why wait until he's guarded to shoot the ball? Now, in order to really understand what's happening, we need to actually look at the pixels. Okay? So let's take a look at the same possession from the perspective of the SportView video recording. Okay? So there we see that he has to bend over in order to recover a poorly placed pass, right? So appearance is revealing. And it shows that, he had to bend over to recover the ball, right? And he wasn't in a shooting position until his defender had closed out, okay? So by distilling the shooter's appearance down to his body pose, we can represent this using a low-dimensional and interpretable space. Great. How exactly do we capture this pose? Well, Vicon uses motion capture, which basically means they put markers on body joints before recording footage, okay? The known locations of the markers, as well as the ease of detecting these markers, makes it easy to reconstruct the body pose. Well, that's not really going to be possible in the NBA, right? That's pretty invasive. Okay, there's also the Kinect, which uses a depth sensor to help recover pose. All right, well, there's one small problem. These sensors have somewhat limited range, right? And it's also not practical to set up an array of these sensors around the court. Okay, what about pixels to pose? Over the last 5 years, progress in computer vision has really skyrocketed with deep learning and the hardware to make it feasible, GPUs. Right? So right now, the state of the art in computer vision can take this image of two ballet dancers and correctly output their body poses using some computer vision machinery. Okay? Let's see how this does on some broadcast footage. It looks pretty good. Of course it makes mistakes. But keep in mind that pose detection on this kind of data is only going to improve, right? The method applied here is, 1, not trained on any basketball-specific data, and 2, it's run per frame, which means it has no idea that the pose of players needs to be temporally consistent. Okay? So, given 2D body pose, what can we do with it? All right, the remainder of this talk is going to be in two parts. The first part, I'll talk about using the skeleton representation of body pose and estimating 3D pose. I'll introduce a method for aligning the poses from different shots and discuss what types of things we can learn from this data. In the second part of this talk, I'll introduce a novel representation of body pose that's based on movement attributes, and I'll discuss some analyses of shots in that space. Okay, so part one, let's look at the skeleton pose representation. This is your typical skeleton with 14 body joints. And if we mark those joints on a player in the broadcast view, and then extract out that pose. Okay, using Amazon Mechanical Turk, we labeled roughly 800 three-point shots in a 3-second time window around the shots. Let's take a look at an example of this. Okay, so here's one of Damian Lillard's three-point shots with his body pose labeled. Let's see the same example, but just his skeleton. So you'll notice that sometimes the body joints are outlined in white, and this corresponds to instances where those body joints are occluded. Okay, let's see another example, this time one of Klay Thompson's shots. And let's see his skeleton. Now, Klay and Damian both took shots from different spots on the court. And because of the camera view, even though they went through similar poses in real life, their 2D pose looks nothing alike, okay? 2D body pose is not able to be compared, right? Instead, we need to estimate the 3D pose, right? In 3D, we can compare these shots, okay? Estimating 3D pose from 2D is actually a really hard problem, right? You're trying to estimate more dimensions than what you started with, and one of the challenges is that different 3D poses can project to the exact same 2D pose, right? So there's an inherent ambiguity when you're going from 2D back to 3D. Okay, well, fortunately, there's a large body of work on this, and we used one recent method, which has a lot of math behind it. I'm not going to go into the details. Let's see some results. Okay, so here we have the broadcast view. Here's the extracted pose. And here's the 3D pose. All right, so now that we have the 3D poses, we need to spatially align them, right? And we do this by first spatially aligning all the release points. This gives a transformation from one pose to another. And we apply that transformation to the other poses in the corresponding shot. Okay, this is also more math. I'm not going to go into it. Let's see some results. Okay, so if we look at the average release point of the Warriors' death lineup from last season, we see that their release points are different. And more importantly, we see that the average release point in their made shots, which is in red, is different from the average release point in their missed shots. Okay? Similarly, the average body joint standard deviation is also different for these players. Okay? All right, now we have spatially aligned poses. How do we temporally align them? We use something called dynamic time warping. It also has more math, but I'm going to give some intuition behind it. Okay? Suppose you have two signals. And for example, these could be the z-coordinates of Klay Thompson's and Damian Lillard's right wrist during their shots. The goal of dynamic time warping is to align similar points, right? Like these, and to align all the corresponding points. right? So let's see some results. This is an example of, this is kind of unfortunate. So I'm presenting off of the laptop that's here, and my laptop here plays this video, but this one, for some reason, isn't playing. If you could press play back there, that would be fabulous. Yeah, here we go. So this looks pretty good. It matches up the time when they are reaching to receive the pass, the time when they're jumping and releasing the ball, and the time when they're moving backwards after they land. Okay. All right. Now, if we cluster all these spatially and temporally aligned poses, for a single player, we can see some states that start to emerge. Okay? So on the left, we have the z-coordinate of one of Harrison Barnes' body joints in 5 made and missed shots. And the colors correspond to the learnt states. So qualitatively, we see that blue is roughly when he's pivoting, red is when he's set, black is when he's running or walking or hopping, and magenta is his jump and release. Okay? This is pretty cool. We didn't tell the computer what running looks like. We didn't tell it what a jump looks like. We didn't tell it what a pivot looks like. Okay? But these states emerge from clustering. Now, if we really want to drill down and see how movements correlate with made and missed shots, we need some finer grained movements captured. Things like a left step, a right hop, jumping from one leg. Okay? And that's what I'm going to talk about in the second part of this talk. Here, we record discrete attributes that describe the movements of a player's shot. Okay? But what states do we want to capture? All right, so here we see Steph Curry laterally moves before he has possession of the ball. Okay? We see that he really had to reach for a bad pass, and his right leg swung forward during his shot. All right, let's see another example. So in this case, he gets a good pass, he dribbles a little, steps back, and lands with both his feet together. So, motivated by these examples and other examples, we divide the timeline of a shot into 5 phases. The first phase is the time before a player has possession of the ball. The second phase is the time when he has the ball, but before he's taken the shot. The third phase is that final moment immediately before his shot. The fourth is his jump and release. And the fifth is after the landing. Okay, and these are the skeletons in those different phases. And we want to build a discrete representation of the movements in each phase. And this forms the basis of our attribute dictionary. Okay, so we labeled 17 attributes in 1,500 three-point shots from 29 of the Warriors games. All right, and these are attributes that are specific to the different phases, and each attribute takes on one of its possible set of values. Okay? So one thing is that shot context can bias analysis, right? So we partition the shots into tough versus open shots by using the probability of the shot success, right? And then we pairwise compare the distributions of each attribute in 4 settings. Tough shots that are made versus missed, open shots that are made versus missed, and these two kind of capture the movements that may correlate with made and missed shots, normalized for game context. And then we look at missed shots that are tough versus open, made shots that are tough versus open, and these two comparisons kind of capture movements that correlate with open and tough shots normalized for shot outcome. Okay? Let's see some examples of these. So that is a pretty tough shot, right? Let's see another example. So I don't think it gets any more open than that. All right, one more example. Okay, and that shot's kind of somewhere in the middle. We don't use these shots in our analysis. Okay, so now I'm gonna highlight some of our attribute analysis. We'll look at overall balance, where the values can be balanced versus not balanced. Then we look at tough, made shots versus missed shots. So we compare these attribute distributions using the Pearson's chi-squared test. Okay, we get really low p-value. So this difference is statistically significant. All right. Now we do the same thing. Open, made, and missed shots. Well, these have a really similar distribution. Missed, open, and tough shots. Okay, this distribution is statistically significant, the difference. Okay. Made, open, and tough. These are relatively similar. Okay. Similarly, we look at other attributes in different phases of the game. So movement type, before they have the ball, maybe they already started with the ball, so it's not applicable. They set, walk, hop, run. Okay, in made versus missed shots, this distribution is statistically significant. So it matters how they're moving before they get the ball, and also what direction they're going before they get the ball. Okay, and something else that was interesting, open shots have a higher percentage of bad passes. All right, and similar statistical significance is observed when comparing the distributions of these attributes of the other attributes in different phases of the game. I won't go into the details, but please stop by our poster or see our paper for the numbers on this. Okay? So up until now, the analysis has been, we've aggregated the analysis over all players, right? What happens if we look at some player-specific analysis, right? So these bars correspond to the balance of 12 different players in tough and open shots, right? So on the left, we see the percent of tough shots that are balanced. And on the right is the same thing, but open shots, right? And what we see is they all have different distributions, right? At one extreme, we've got James Harden, who is almost always balanced. And at another extreme, we have Steph Curry and Damian Lillard, who are often off balance, even in their open shots. Okay? So I guess the key takeaway, this is just the start, right? We really need some player-specific analysis for this, and Steph Curry is kind of a great example of this. His average shot is tougher, and yet he's more off balance than the average player, and yeah, thank you.
Questions?
Hi, very enjoyable. One question that came up early is that you have stats, sport view, multiple camera angles, and you presented the monocular view to get the kind of body shapes. Do you know if there's much of a change in performance from one camera versus multiple? if you were to do the same thing for structure?
So we did our analysis in the broadcast view, and from multiple camera angles, it's obviously much easier to get body pose, but right now the resolution isn't really there for those views.
Hi. So when you're talking about the tough plays, are you considering, or tough shots, sorry, the shot clock? Because, you know, one of the plays that you showed, the shot clock's going, and so Steph Curry makes, you know, takes the bad shot, even though maybe he could have spent more time to get ready.
Yeah, so there are a lot of factors that go into the tough shot score, including the shot clock, the position of the players, the position of their defenders, these kinds of things.
Okay.
Think we have time for one more. Anyone?
So, you know, you started this off with the example of the, you know, the pass that was dribbling along the ground, right, that led to the harder shot that wasn't apparent from the initial look at the XY data. And I'm wondering if you have attempted to, like, circle back to that problem, right? It's like, okay, now does your tough account for, you know, the quality of that pass, right? We know the defender at the time he took the shot
So
was
pass
now
quality,
closer.
pass quality was something that, one of the attributes that we looked at.
You mind taking one more?
Sure.
I just have a question about the second part of the talk, the data. Is the data being labeled directly from the body pose work in part 1, or is it being manually labeled?
It's manually labeled.
Great. Thank you very much.
Thank you.